Welcome back to this mini lecture series on quantitative economics. You're watching Honey of Knowledge and this is Ashish Gourav. In the first video, we introduced this magical equation of econometrics. Now, when can we use this equation? There are multiple aspects to it. And one basic idea here is to understand whether x and y are linearly associated or not. To understand whether there is a linear association between them, we need to look at something called correlation or correlation coefficient. How do we get these diagrams? These diagrams essentially are a kind of scatter diagram or scatter plot. So let's look at how to get these scatter plots. A pretty standard XY graph. Now what you are going to do is collect all the XY pairs. Let us say you have 100 data points. Now what are data points? You have 100 XY pairs. So you could have X1, Y1 to X100, Y100, which means you have 100 pairs of XY values. And what you do is you plot on this XY graph. Now, after you get this diagram is known as a scatter plot or a scatter diagram. If you look at the diagrams 1 and 2, they are perfect examples of positive and linear association. 1 for positive and 2 for negative. And if move from 3 to 8, they are related but not exactly linear in nature. And if you look at diagram 9, there is no relation whatsoever. You can see all the points are scattered throughout. Now, even if you look at diagram 3 to 6, they have some kind of linear association. Not perfectly linear, but some kind of linear. But 7 and 8 diagrams have no linear association. They have an association, but remember, correlation must ideally measure linear association. It should not measure your non-linear association, because I have to capture the linear association between x and y. This is one of the factors which decide whether we can use this magical equation of econometrics. Our recap: 1 to 6 we can measure correlation. 7 and 8 no, we can't. Having discussed the idea of scatter plots and how we can look at scatter plots to understand whether there is a correlation or not, how can we quantify it? How can we calculate some kind of a number which gives you that idea rather than just looking at scatter plots all the time? So let's formulate that process. So in an ideal sense, correlation should be able to measure positive and negative relation. So it should report a positive number when there is a positive relation, something like this, and it should give you a negative number when there is a negative relation, and it should give you a value of 0 if there is no relation. So how do we construct this kind of a metric? What I have done over here is found out the sample mean and divided the XY graph into 4 sections. This section is the area where x values are greater than the x mean and y values are also greater than the mean of y. Over here, x values are less than the value of mean of x, but y values are greater than mean of y. And if you come here, both x and y are lesser than their means. And over here, x is greater than the mean, but y is lesser than its mean. This is kind of a quadrant division which you do in your xy system. But this is not a normal quadrant division, because a normal Cartesian coordinate system division would be something like this. Whole thing would become 1, this become 2, 3 and 4. So this is a modified kind of a quadrant for our analysis. Now, if we look at this product, what is this product? This product is measuring the extra value of xy on top of its mean. So essentially this is delta x into delta y. Delta meaning change. So change in x multiplied by change in y. So how do we calculate this change in x? Xi minus x bar, or the point value of x minus the sample mean of the x. That is your deviation of x, and deviation of y would be point value of y minus the mean of y. If you multiply this, what will happen to these areas? Just look at this part first. Both x and y are greater than their means. So xi minus x bar is greater than 0. Similarly, yi minus y bar is also greater than 0. So if you multiply two positive numbers, you will get positive. So this is positive. If we move to second quadrant, xi minus x bar by definition has to be negative here, because we have moved to the left of our sample mean of x. But still yi minus y bar would be positive. So one negative, one positive, multiply them, you will get a negative number. So this area would be negative. Come to quadrant 3. In quadrant 3, both the values, both the deltas, both the deviations are negative, because if you move to the left, x decreases. If you move to the bottom, y decreases. And both have decreased from their sample means. So negative into negative, positive. So quadrant 3 is positive. What about quadrant 4? You can figure out the same kind of analysis and realize that even this is negative. So quadrant 1 and quadrant 3. Let's first understand what happens when you're in quadrant 1 and 3. If you go from sample mean to quadrant 1, you will have to move something like this, which is kind of a positive linear relation or just simply positive relation. It could be linear or non-linear. If you move from sample mean to quadrant 3, now this would be something like this. Again, this would be positive in nature, because remember, for positive I need this kind of a shape. If you increase x, y should also increase. If you look at quadrant 2 and 4, if you go from sample mean to 2, you will get this kind of a graph. And if you go from sample mean to fourth quadrant, you will get something like this. So if you look at these lines, you can understand that there is a kind of a pattern here. That pattern is like this. If you increase x, y falls. So this is your negative relation, which gives you a hint that this is measuring correlation. So this is giving you an idea of correlation. But this is not correlation coefficient or correlation. This is not how we measure correlation, we modify this. So let's move to that. Let's look at a recap of this. Quadrant 1 and 3, product of deviations, positive, positive relation, positive correlation. Quadrant 2 and 4, product of deviations, negative, shape like this, negative relation or negative correlation. A recap of elementary statistics which you might have read. Covariance between x and y is defined as the sum of product of deviations, this thing numerator, sum product of deviations upon the number of observations. And variance is defined as square root of this quantity, sum of square of the deviations upon n, the number of observations. Similarly, the variance of y, sigma y, is equal to square root of sum of the squared deviations in y upon number of observation. If you know covariance in xy, variance in x and variance in y, we can move ahead to finding the simple correlation coefficient. So covariance will be positive when we have a positive linear relation, and covariance would be negative when we have a negative linear relation, and covariance will be 0 when we have almost no linear relation between x and y. And if you look at the variance in x and y or variation in x and y, sigma x, sigma y, they would always be positive. So they are not going to affect your sign of simple correlation coefficient, even if I introduce them in some kind of a product or division. So let's look at how we introduce sigma values into covariance to get to simple correlation coefficient. Simple correlation coefficient or rho xy is covariance of xy upon the product of variance in x and y. I'll recap. Rho xy or simple correlation coefficient is covariance of xy upon variance of x into variance of y. Let's give it symbols. So in place of variance x and variance y, we can also write sigma x and sigma y. So to sum up, correlation coefficient is covariance in xy upon sigma x, sigma y. Now I'll give you a bit of homework. Correlation in xy has a range. So what is the range of values this can take? Think about it. I would give you the answer but not the solution. Correlation in xy, rho xy minus 1 to plus 1, or in other notation, rho xy is from minus 1 to plus 1. That's it for this mini lecture of econometrics. We will talk about some other concepts in a different video. Now hit that subscribe button and click the bell icon and like this video. Bye.